Hi, I'm Jim Heffron. These are my lessons in Calculus 1. So we're starting on Chapter 4. We learned a lot of techniques and a lot of ideas in Chapter 3 about what the rate of changes of functions are. And now in Chapter 4, we're going to apply those to try to make some conclusions. An example is that in the previous day's slides, we looked at graphing without calculus, and we were able to spot when there were local optima, local high spots, local low spots. And we said, well, we don't yet have the tools to find them. Okay, well, you can tell by today's title that we're going to find the tools to find them today. Okay, great. Let's get started. So here's the definition that we saw not too long ago. So just as a reminder here is that if you have a number lowercase a whose output here is associated with the point capital A, then it will be called a local maximum if it's a high spot in the neighborhood, meaning that lowercase x's near to lowercase a give values that are slightly less than the value of f of lowercase a. All right, so that's a local maximum. Capital C also is associated, is a local maximum here, and capital B is a local minimum. We sometimes are interested in which of the local maximums are absolutely the highest spot, and so we'll call those absolute maximum or sometimes global maximum. So in the picture as it's drawn, it appears that capital A is a place where the graph is as high as it gets over the entire domain. It appears that capital C and capital B are, they're local optima. Okay, so they're associated with local max or local minimum numbers. I want to make a point about local optima that everybody has noticed. So I have here two folks playing baseball, and the batter hits the ball, and the ball rises, and then seems to hang there just for an instant. So it's instantaneously stationary. It's neither rising nor falling, and then of course it starts to fall. So the maximum, in this case the optima is the maximum is associated with a vertical velocity of 0, with the ball just hanging there, just being stationary just for an instant. Okay, and that observation from the prior slide is called Fermat's theorem. For any function, an optima must occur where either f prime is equal to 0, that is to say where the graph is neither rising nor falling, or where f prime of c doesn't exist. And I have the two pictures at the bottom of the slide. The intuitive argument here is that a function is approximated by its derivative if we have if we're at a point lowercase c where the function's derivative is positive, then for x is near to c, f of x is a little higher than f of c. So we think that c is not a local maximum. Anyway, the definition down here is that a stationary number is an input where f prime of x is equal to 0, so that when the ball is hanging there, neither rising nor falling, we think of that as being stationary. So a stationary number is an input where f prime of x is equal to 0, and then a critical number is an input where either f prime of x equals 0 or f prime of x doesn't exist. And so in this picture here, we're looking at a stationary point. X equals 0 is a stationary point because the derivative is 0 there. And here, stationary point, also a critical point. Oh, I called it a stationary point. I should have called it a stationary number and should have called it a critical number. It's not the crime of the century, but I told myself to do that, and I didn't do it, darn it. And likewise here, this is going to be a critical number. Our interest in critical numbers is precisely that Fermat's theorem up here precisely says that those are the places where optima occur. So if we're looking for an optima, you want to look among the stationary numbers, among the critical numbers. Okay, it doesn't mean you found it, but that's where you want to look. So critical numbers are candidates for optima. At a critical number, there may be a local optima, and I drew a picture here of a critical number where there's a local optima, it's a local max, it happens to be. I also drew a critical number where there's a local optima, it happens to be a place where the derivative is not defined. So derivative of 0 and derivative of not defined are the places where you can get a local optima. But it's also possible that if you have a critical number, if it is the case, for example, here that the derivative is 0 because the function rises, pauses for just an instant in its rise, and then resumes the rising, or it can be the case that the function has a vertical tangent, and of course a vertical line doesn't have a defined slope. So just because you found the critical numbers doesn't mean you found all of the local optima. But nonetheless, if you're looking for local optima, you want to look for critical numbers, and then you've narrowed down the candidates to a small number of cases. Okay, so you know how I like to work. I like to give folks a concept, and then, if possible, give them an opportunity to work with it for just a minute or two to make sure they've got it before they go on. Okay, great. So let's have a whack here. It says, for each function, find the critical numbers. And of course, I'm going to suggest that you pause the video and try it. Take out a piece of paper, give it a try. If you get stuck, I'll show you the answer. If you don't get stuck, good for you. Okay, so the derivative here is x squared minus 5x plus 4, and I made it so that it factors easily into x minus 4 times x minus 1. The derivative is always defined. Derivative is always defined. There we go. Always defined. And so the only case where you're looking for critical numbers, you're just looking for places where the derivative is 0. So the derivative is 0 at x equals 1 and x equals 4. We call those places the stationary numbers. So the stationary numbers are entirely the critical numbers. There are no derivative undefined possibilities. Okay, next up, please. Great. So same thing. I'm going to take the derivative and worry about where is it undefined and where is it equal to 0. So there's the derivative. G prime of x is when you end up multiplying the 3 and 2 together, you get 6x times x squared minus 1 quantity squared. So where is it undefined? Where is it equal to 0? Well, it's always defined. Always defined. So we only need to worry about zeros. And so when you look at this expression, you say to yourself, well, x equals 0 or x equals plus and minus 1. And so those are critical numbers. There are only stationary numbers. There are no places where the derivative is undefined. So I must be going to do an example where the derivative is undefined. So you see it sitting right there. So please, one more. We'll try practice. Okay, great. So of course a quotient, and I'm going to apply the quotient rule. Here it is. Remember, in the quotient rule, you write the denominator squared on the bottom. Denominator times the derivative of the numerator, numerator times the derivative of the denominator, gather terms, and you find yourself over here. I'm asking where is it equal to 0 and where is it undefined. So a fraction is equal to 0 where its numerator equals 0. This numerator is never 0. So we have no places where the derivative is 0, no stationary points. Fine. What about where is the derivative undefined? And it's, of course, where 5v minus 1 equals 0. And that only happens when v is 1 over 5. Okay, so you solve 5v minus 1 equals 0, you end up with v equals 1 over 5. So that's only a single critical number. Some functions have lots of critical numbers, some functions have none at all. Okay, so I want to talk about the phenomena of optima, and I want to want to say some things about it. We've spotted that if we want to find optima, we'll look among the critical numbers, but there's some things to say about optima. First of all, this function has a critical number, very familiar function, of course. This function has a critical number, but no maximum or minimum. There's no local maximum, there's no absolute maximum, there's no local minimum, no absolute minimum. We all know that if you take the derivative of f, 3x squared, and plug in x equals 0, you do indeed get a stationary point. 0 is indeed a stationary point and therefore a critical point, but there's no maximum or minimum. So just because you found a critical point doesn't mean you found an optima. Second, here's another example of a cubic. This one's just a little bit messier. It's got 3 different roots. It crosses the axis at +1, 0, and -1. And so, when you multiply it all together, you get x cubed minus x. The derivative is 3x squared minus 1, so the critical numbers are at x equals plus and minus square root of a third. Oops, made a mark. Plus and minus square root of a third. There's one of them right there, and there's the other one right there. Okay, so it has a local max. You can see it at negative square root of a third. It has a local min at positive square root of a third, but it has no absolute max and no absolute min. So just because you've got at least one local max does not mean you have an absolute max. This function just keeps going up and up and up and never attains its absolute maximum. Here's another example. This function has a single maximum at x equals 0, and it achieves it. But it never achieves a minimum because it has a horizontal asymptote here of 0, so it's falling, but never gets all the way down to 0. So a function can have a high spot but no low spot. Alternatively, a function could have a low spot but no high spot. Here's an example of a function that has neither a highest spot nor a lowest spot. Again, familiar function 1 over x, where x is greater than 0. The function's value never reach infinity, and its values also never reach y equals 0. So optima are somewhat complicated behavior. I mean, not tremendously hard, but they're somewhat, they aren't 1, 2, 3. They're things a person needs to think about. Here's a case that I want to talk about for just a second because although it's a simple case, it illustrates some very important thing. I took the graph from the prior slide, 1 over x, and I looked at it, instead of over the domain where x is positive, I looked at it over the domain, the open interval from 1 to 3, and you'll remember that open interval means not including the 1 and not including the 3. This function does not have a high spot. It just doesn't. If you stand here at 1.01, that's not the highest spot. If you stand here at 1.000001, that's, the associated y is not the highest spot. And likewise, it has no lowest spot. So this function does not have an absolute maximum or an absolute minimum. Doesn't have a local either. But anyway, it does not have a high spot and does not have a low spot. So the failure to have an optima isn't just about infinity here. The failure to have an optima has something to do with the openness of the interval. The fact that you can walk closer and closer to one but never reach one is the reason that you don't have an optima here. You don't have a high spot. So to ensure that a function attains its optima, if we're trying to, figure out what's the absolute most profitable way to run our business, or to ensure that a function attains its optima, we have to think carefully about not just the function, but also about the input interval. So there's something special about intervals that are closed and bounded. The interval in the prior slide that was open doesn't allow us to obtain our optima. So the theorem goes that a function that's continuous on a closed and bounded interval attains its maximum and also attains its minimum. A function that is continuous on a closed and bounded interval. There's something special about closed and bounded intervals. Starts at some point A, ends at some point B, and includes both the endpoints. So a function that's continuous on a closed and bounded interval must attain its maximum and must attain its minimum. So what we then have is a strategy for finding optima. If we're given a function that's continuous on a closed and bounded interval, you find the critical numbers and you write down the value of f of c for all those c's. You also write down f of the start point and f of the end point. That gives you a table with a bunch of numbers in it. The highest number is going to be the highest value. The lowest number is the lowest value. You found the maximum. You found the minimum. Ties can happen. But anyway, the point is that there's something special about intervals that are closed and bounded. It's the closed and boundedness that makes this work. Continuous function on a closed and bounded interval must attain its optima. There's something special about closed and bounded. Okay, of course we're going to do examples. Of course we are. So here's an example of a function that is continuous, and I'm looking at a closed and bounded interval. So it's got to attain its optima. So my plan, the strategy from the previous page, is to figure out what the critical points are, find the critical numbers between 1 and 3, including the 1 and including the 3, make up a table, and whatever is the highest one is the highest one. Whatever is the lowest one is the lowest one. Okay, so the derivative minus 2x plus 3 is always defined, and it's 0 at x equals 3 halves. So there's a single critical number. With the interval endpoints, that makes 3 numbers to check. So I plugged in the 1 here, the 1, I plugged in the 3, and also plugged in the critical number. I made a table. The table was 3 lines. I figured out what is f of 1, what is f of 3, what is f of 3 halves, and I'm doing sort of the most simple-minded thing possible, and it works. The highest one is the highest one. It's 1/4. Can you see it right there? And the lowest one is the lowest one. It's minus 2. Notably there that the minimum falls, the absolute minimum falls at an endpoint, so you have to check the endpoints. It can be that the maximum or minimum occurs at an endpoint, or both occurs at an endpoint, so you have to check those. So this, if you're thinking this is simple-minded way to approach it, yes, it is simple-minded. But again, just to click back here, it would not work if the interval was open. What makes this work is that the interval was closed and bounded. Okay, so another couple here, just to try. X squared minus 3 times x to the 2/3 power, and the closed and bounded interval 0, 2. Okay, great. So the derivative is, there's the derivative here. The derivative is this expression right here. I end up with a fraction, x to the 1/3, of course, cube root of x, on the bottom of the fraction. It's not defined at x equals 0. It's the derivative is not defined at x equals 0. It's 0 when x is plus and minus 1. And I don't need to worry about what happens at minus 1 because that number's not in the interval, So I only need to worry about the critical numbers and the endpoints. So I end up with a list of size 3. It happens that one of the critical numbers is also an endpoint, so don't check it twice. That would be silly. But I get here a height of minus 2, a height of minus 0.76, and a height of 0. So it seems to me that the minus 2 is the minimum, and the 0 is the maximum. Okay. Okay, so it is the closed and bounded nature of the input, but nonetheless, once we do that, take the derivative, figure out where it's 0, and also figure out where it's undefined. I have to tell you that, like given a quiz or exam, the most common mistake with these is to check where it's 0 and forget to check where it's defined or undefined. That's a very common mistake here. So when I give an exam anyway, I make sure that I always include one of the not defineds. Okay, practice, of course, the way I like to work is to give you an opportunity for some practice. So we're going to optimize that function clearly continuous, because it's a polynomial, on a closed and bounded interval. Okay, give you a second and then to get started, and then I'll, you can pause the video, and then I'll show you the answer. Okay, great. So I took the derivative here and got 6x squared minus 30x plus 24. That's always defined. So I only have to worry about where is it equal to 0. When I set it equal to 0, I got x equals 1 and x equals 4. That gave me 4 numbers to check, the endpoints 0 and 6, and also the critical numbers 1 and 4. Took out a calculator and found the highest value was the 43 and the lowest value was the minus 9. And I drew the graph just to give a person some sense of what's happening, so I do indeed get minus 9 and 43. Okay? Okay, great. So we've talked about some things that the graphing without calculus section made clear that we need. We need to be able to find what are the high and low spots, the local high and low spots on a graph, and now we have a good plan to find them. Is that we worry about what are the critical numbers, and they're the candidates for local optima. Okay, very good, very good.